talking about percentiles last time in section 3.3, and we have looked at just the percentile graph, and then of course how to use the formulas to calculate our percentile. So that was actually the last thing that we had stopped, as we had seen examples from our textbook for that. So what we want to do today is actually get started with quartiles and deciles. So, you know, of course, quartiles and deciles are percentiles essentially, but they are just at different levels. So as you can see over here, when we're talking about quartiles, we're talking about Q sub 1, Q sub 2, and Q sub 3. So Q sub 1 basically corresponds to the 25th percentile. So if you think in terms of quarters, so the first quarter section of our percentile would be at the 25th percentile. Quartile 2 would correspond to the 50th percentile, and quartile 3 would correspond to the 75th percentile. And you can kind of see on this number line over here how we're breaking up our data set here. So quartile 1 would of course be right at 25% of the data values would be falling beneath it, and 75% would be above. At quartile 2, of course, we would have 50% of the data values below it and 50% above. And at quartile 3, we would have 75% of the data values below it and only 25% above it. So that kind of gives you a nice visual over here. So as I was mentioning last time, you can use the same calculations we did for finding percentile and finding these quartiles. You would just need to make P equals 25 for quartile 1, P equals 50 for quartile 2, and P equals 75 for quartile 3. Or you can use this procedure table over here, which might be a little bit easier than, you know, using the percentile formula. So same thing, we would still need to arrange our order from lowest to highest. So that would still be a requirement here. Now, for finding quartile 2, it's the same as finding the median for your data value, so that would be the same as quartile 2. Once you find that median or quartile 2, then you can look at all the data values that fall below this quartile 2 value and find the median again, and that would come out to be your quartile 1. Then look at all the data values that fall above quartile 2 and find their median again, and that of course would be the value for quartile 3. So technically what you are doing is you're finding the medians for all of these quartile 1, 2, and 3 values. So start by finding your quartile 2, which would be our median. Well, there we go. So find your median for the entire data set, which is quartile 2. Then we take the lower half of our data values, find the median again, which would be quartile 1, and then for the upper half of our data value, same thing, find the median again, and we would have quartile 3. So that is actually going to be a lot more straightforward than going through the formula. So we're still using the same example from our exercise 4, which was of course our traffic violation. So just to show you the example here, this is the number of traffic violations recorded by the police department over a 10-day period. And so again, arrange our data values in order from smallest to largest. Then as you can see, these are over a 10-day period. So you would be finding the median between 18 and 19, which of course comes out to be 18.5. So this will be our median for the entire data set, but that's also going to be our quartile 2. And 18.5 would of course fall right here halfway between, which means the first 5 numbers, 9 through 18, we find the median again, and in this case, of course, the median comes out to be 15, so that's our quartile 1. Then you take the second half of your data set, which is 19 to 25, find the median in that, and of course, that median comes out to be 22, which is going to be our quartile 3, and then of course, you can see we end up getting those 3 quartile values. So that's why just finding the median of our data sets obviously works a lot faster instead of going through the formulas. So that's the example for finding our quartiles. Now, one of the other calculations that we also do is what we talk about in terms of the interquartile range. So basically they're saying, in addition to dividing the data set into 4 groups, quartiles can be used as a rough measure of variability, which means, again, you can kind of use this in the sense of dispersion, how spread out our data is. And they're saying this measure of variability uses quartiles, and that's called the interquartile range. And they are basically saying it is the range of the middle 50% of the data values, because that's actually going to be the difference between our quartile 1 and quartile 3. So when we're talking about the interquartile range, you're actually talking about the values going from quartile 1 to quartile 3, and this is what as the interquartile range. Okay, so interquartile range is basically simple subtraction between quartile 3 and quartile 1. So if you just take a look at this example over here, 22 was our quartile 3, 15 was our quartile 1 value. So if you take the difference between those numbers, you end up getting an interquartile range of 7. And these calculations will actually play a big part in section 3.4 when we start talking about Boxplot. So we'll be looking back at these calculations in that section. So basically the idea here is just like standard deviation. The more variable our data set is, the larger your interquartile range value will be. The less variable the data set is, of course, the smaller the interquartile range value comes out to be. And in that same sense, you can also have deciles. And you know, if you think of deci, we're basically breaking this up into groups of tens. So again, you would have your deciles as D sub 1, D sub 2, all the way to D sub 9. And you can see this horizontal scale again over here. It's of course breaking it up into sections of 10% each. So D1 would basically mean 10% of the data values fall below, 90% would fall above that number. And you know, that would be the same thing. So again, you should notice that D5 over here, or D sub 5 is going to be the same thing as the 50th percentile. And then, you know, of course, D3 would be at the 30th percentile and that kind of thing. So you can kind of see that in the note over here. We're kind of talking about them. They're saying deciles can be found by using the formulas for the percentile. So the percentile formula we looked at last week. Some comparisons they are showing over here. Your deciles of D1, D2, all the way to D9 would correspond to the 10th percentile all the way to 90th percentile. Quartiles, of course, we just talked about them, are going to be in terms of the 25th, 50th, and 75th percentile. But your median can be calculated by using the 50th percentile, quartile 2, or decile 5, basically. So all of those would correspond to the same exact data value. So it's really just percentiles that are being broken down into quartiles and deciles. So just a summary of all the different measurements of positions over here you can see in this table. So let's take a look at a couple examples where we need to calculate these deciles, quartiles. Let's see what kind of example we have here. This is using percentile. Okay, let's see, this one is asking us for the percentile. Let's look at 25 over here. They're talking about, let's see, so we've got the data for a recent year show the taxes in millions of dollars received from a random sample of 10 states. They're asking us to find the first and the third quartiles and also the interquartile range. So the first thing we actually need to do is arrange this from the smallest to the largest data value. So let's see what that order comes out to be. Okay, so what order would we put these numbers in? Okay, let's see, we've got Jesus, so we've got 6, 11, and 11. Okay. We got 6, 11, 11. And then you have 13, 15. Okay. And then we're going to 24, 25. Okay. Let's see, 24, 25. So that leaves us with basically our 30s. So that would be 32, 36, and 71. Yeah, very good. Alrighty. And they said for 10 states, so that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, we've got all 10 of our numbers over here. Okay, so the first thing we'll do is, well, let me go ahead and clear those marks. Okay, let's go ahead and find our median, which would be equivalent to our quartile 2. What do you think that number comes out to be? Let's see, Lily, you've got 19.5. Yeah, because we're talking in terms of position. So, you know, you've got 10 data values over here. So if we just talk about the position formula, that would be n plus 1 divided by 2. 10 plus 1 is 11. 11 divided by 2 would give us 5.5, which means we're looking at the 5th and the 6th position. So that would be the 5th and the 6th position. You can count from either direction and we will end up with that. So of course that means we are taking the average between 15 and 24 divided by 2. And like you guys said, Jesus and Lily, we've got 19.5 as our median. So it would be right over here. 19.5. So of course then that means to find quartile 1, we would find the median in the first half of our data set, and then for quartile 2, we would be going to the second half. So for quartile 1, what will you have as the median for the first half of our data set? Yeah, very good, guys. It will be 11 because now we have 5 data values in that first half. So of course your median is going to be the centermost number, which of course will come out to be 11. So that's going to be quartile 1. And then what about quartile 2? Sorry, quartile 3, not 2. Alrighty, very good. You have 32 as the answer because again, you have 5 data values in the second half and the centermost value is going to be 32. So that's going to be our quartile 3. Alrighty, so now that we have our quartile 1 and quartile 3, what is the interquartile range going to be? Yeah, very good. You are doing 32 minus 11. So of course that would come out to be 21 over here. You can see these are pretty straightforward calculations, but did you guys have any questions on any of these? You okay? Alrighty, let's see. This one is also asking us to find quartiles. Do they have anything on deciles? Doesn't look like it. Alrighty, no questions on deciles, but obviously, as you can see, you can just use the percentile formula. Let me just show you that really quickly. So you can basically use this percentile formula to calculate your deciles, except you would be doing them at increments of 10. So decile 1 would be the 10th percentile, decile 2 would be the 20th percentile, and so forth. Now, one of the other things that kind of helps us in this measure of position, of course, is also how the outlier affects our calculations, right? So any extreme high or extreme low value is what we call as an outlier, compared to the rest of our data set. So they're basically saying an outlier can strongly affect the mean and standard deviation of the variable. And we saw with some of those examples in section 1 and 2 for that matter. They're saying since these measurements, the mean and the standard deviation are affected by outliers, they are called non-resistant statistics. Oh, come on, buddy. There we go. Okay, so mean and standard deviation are the non-resistant statistics. The median interquartile range are not affected as much by the outlier, so we call them as the resistant statistics. So that's your mean and interquartile range, and then mean and standard deviation would be, of course, part of the non-resistant because they change easily, they give way easily. So they're saying sometimes when a distribution is skewed or they contain outliers, it would be better to use the median for your average or your measure of central tendency, and use the interquartile range instead of the standard deviation for your measurement of variation or your measurement of dispersion. So kind of keep that in mind as you're going through different examples. They are saying that basically the median and interquartile range can be used for a more accurate description of the data instead of the mean and the standard deviation. So just again, how can we identify if our data set actually has an outlier? Sometimes, it's easier to look at your data set and something may jump out. But the other thing we can do is follow this procedure over here. So again, start by arranging the data in order, going from the lowest to the highest. And then, of course, we want to go ahead and find our quartiles 1 and 3. Find the interquartile range. Now, once you have done this calculation, what we do is we multiply the interquartile range by 1.5, and then taking our quartile 1 and quartile 3 measurements, we're going to be subtracting this answer from step 3 from quartile 1 and adding it to quartile 3. And depending on what those numbers come out to be, it actually gives you a range of data values. And if you see a number which is either smaller than this subtraction that we did from quartile 1, so if the number is smaller than Q1 minus 1.5 times IQR, or if you have a value in your data set which is larger than quartile 3 plus 1.5 times interquartile range, then those would be your outliers. So if you see a number which is smaller than the Q1 minus 1.5 IQR, that's an outlier. If you see a number which is larger than Q3 plus 1.5 IQR, then that's going to be an outlier. So if you look at this example over here, we have our data set which is already arranged in order. We are finding our Q1 and Q3. Finding the interquartile range, it comes out to be 11. Multiply the 11 from interquartile range with 1.5, so that gives us 16.5. So you subtract the 16.5 from quartile 1, and that gives us negative 7.5. And we add the 16.5 to quartile 3, and of course that gives us 36.5. So if in our data set you see a number which is smaller than negative 7.5 or larger than 36.5, we would say it's an outlier. So there's not a number smaller, but of course you will see 50 is larger than 36.5. So we would say 50 is going to be an outlier. So that's kind of how this little procedure table actually comes into play to help us identify if you have an outlier or not. And again, we had talked a little bit about outliers in both section 1 and section 2, so you can kind of go back and take a look at that. So before we look at an example, let's go ahead and look at what they're talking about here in these paragraphs. So they're saying there are several reasons why outliers may occur. The data value may have resulted from a measurement or observational error. So that can be a reason for the outlier. They're saying perhaps the researcher measured the variable incorrectly. Your second reason could be the data value may have resulted from a recording error. So, maybe just writing it or typing it incorrectly. So even though you measured it or, observed it accurately, but just as you were writing it down, you switched your numbers or something like that. So that can be an error, which leads to an outlier. They're saying third, the data value may have been obtained from a subject that is not defined in the population. So if a subject was not part of the population, that would also maybe, we had seen an example where we talked about a student who was in like a 6th grade class but was taking a 7th grade class. So that student technically is not part of our population over here. And I think I'm actually talking about that example over here again. So the same thing, they're saying, test scores for a 7th grade class were taken, but the student was in 6th grade and had special permission. So technically this student's grade should not be included in our study. But if you included it and, maybe they scored lower than the rest of their classmates, that could become an outlier. They're saying the fourth reason could be the data value may be a legitimate value that occurred by chance. So it can kind of happen, but again, it's a very rare instance where this will happen. So of course, they're saying the probability is extremely low, but it could be a legitimate value that basically occurred by chance. So, again, that's something we'll kind of have to see as we perform our own experiments and studies. So they're saying there are no hard and fast rules what to do with the outliers. There is not a complete agreement among statisticians either. If they're basically saying if they occurred as a result, as a result of an error, then maybe we want to fix that error. Go ahead and make sure we either correct that answer or basically completely omit that answer, which means don't include it in your data set. So if you know that this result is an error, so go fix it or basically exclude it from your data set. They are saying when these outliers occur naturally by chance, which means no mistakes were made, but they still happened. At this point, I would suggest, and as you can see over there, is try it both ways. Include it in your data set, do the calculation and see what kind of results you get. And do it without including that outlier in your data set. Do your calculations and see what kind of result you get. And then you have to make an educated decision on, does it make more sense to include that number or not include that number? So, again, that would be something we would learn as we go through our calculations. So they're talking about here, when a distribution is normal or bell-shaped, data values that are beyond 3 standard deviations of the mean can be considered as suspected outliers. And we can talk about that when we look at the normal or bell-shaped distributions in chapter 6. Okay, so let's do a couple examples on calculating these outliers. So going back to our textbook over here, let's take a look at, I don't know, part A maybe, and see if that set has an outlier or not. So we've got number 29 over here, set A. Okay, so of course the first thing is to put this in order from smallest to the largest data value. So what will we have? So what is that order going to be for part A? Okay, let's see, you've got 19, 21, 25, okay. What else you guys have? 28, 29, okay. 32, 34, 46, okay. 33, 34, and 46, okay. Alrighty, so that looks like we've got 1, 2, 3, 4, 5, 6, 7, 8 data values in our set over here. So what's going to be our quartile 1 and quartile 3? Because that would mean 4 data values on each side. Okay, you've got quartile 1 as 23 and quartile 3 as 33. Of course, that would be taking the average of these two numbers for quartile 1, so 21 plus 25 divided by 2, and that's the 23. Very good. And then same thing, taking the average of 32 and 34, divide that by 2, which would of course give us 33. Alrighty. Once you have these, we can of course go ahead and calculate our interquartile range. So what will that come out to be, guys? Tyler, yeah, very good. That interquartile range, of course, is just Q3 minus Q1, 33 minus 23, which is 10. Then remember, our next step is to take 1.5 and multiply that by 10, which will give us what? 15. Yeah, very good, Jesus. So basically, we have done the first part where we have arranged it in order. We found Q1 and Q3. We found the interquartile range and we multiplied by 1.5. Now from Q1, we will be subtracting this number, and from Q3, we will be adding it. So from Q1, subtract 15, which would of course be 23 minus 15, and then from Q3, we add 15, which would put us at 33 plus 15. And what do these numbers come out to be? Yeah, 8 for the first one. And let's see, that would be 33, 48. Very good for the second one. So now in our data set, do we have numbers smaller than 8 or larger than 48? Smaller than 8 and larger than 48. No, right? Because your smallest number is 19 and your largest number is 46. So we are well within these two upper and lower limits, if you will, of our data set. So since we are not outside this, basically our conclusion is there are no outliers. So in this case, of course, we wouldn't have to then worry about should we include the number, should we exclude the number, and that kind of thing. Let's do one more example, and we'll do, I guess we'll do part B since we did part A over here. So let's do part B. And there we go. All right, using part B. So let's go ahead and put this in order over here. Okay, so what does this order end up looking like? All righty, Lily, you've got 65, 82, 89, okay, 65, 82, 89, and then let's see, we've got 90, 92, 94, and what else do we have? 97, 100, and 101. Okay, very good. All right, same thing. We need to find our Q1 and Q3. So it looks like we've got 1, 2, 3, 4, 5, 6, 7, 8, 9 data values over here. So that would be 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So this one would actually be our median or quartile 2. So what will quartile 1 and quartile 3 look like? Okay, let's see. Lily, you've got 85.5 and 98.5. Okay, so that means you're looking at the first 4 and the last 4 for your quartile 1 and quartile 3. And then, of course, for quartile 1, we would have to take the average of 82 and 89. Divide that by 2, which is giving us 85.5. Okay, very good. And then, of course, for quartile 3, we would be taking the average between 97 and 100. And that one, Lily, you said is coming out to be 98.5. Okay, very good. And so that means what is our interquartile range then? Yeah, very good, Jesus. It would come out to be 13. And then, of course, remember, we end up taking 1.5 times 13. So you're coming up with 19.5. Alrighty, very good. Once you have that 1.5 times the interquartile range, then we will subtract that from quartile 1. So what's 85.5 65, 66. Okay, very good. Quartile 3 is where we add the number. And you've got 118. Oh, okay, so what can you tell me about this data set? Do we have any outliers? Our lowest number is 66, largest is 118. Yeah, lowest is 66, largest is 118. There we go. Yeah, so since 66 is the smallest data value, that tells us that 65 is outside of that range. Even though it's by one number, it is still outside of that range of 66. Now, since the upper limit is 118, of course, our largest number is 101. So we don't have an extremely high value. We basically just have an extremely low value. Yeah, so very good. We would say the data value 65 is an outlier. Okay, so you can see in both these examples we did with part A, we had no outliers, everything stayed within the limits of 8 to 48. But then in part B, we of course ended up getting 65 as an outlier. So this depends on each kind of data set, but this is a really nice way of, definitely getting an answer whether you have an outlier or you don't. And that's kind of what these examples here talk about. Okay, any questions on this example over here? You guys okay? Yeah? Okay, very good. So that brings us to the last section for chapter 3, which is section 3.4, where of course we're talking about the exploratory data analysis. So they're saying in traditional statistics, data are organized by using a frequency distribution. From this distribution, we can get different graphs like our histograms, polygons, and ogives. And of course, we saw that in chapter 2, which kind of helps us just, show us the shape or what type of distribution we have. So you can kind of look at that. They're also saying, in addition, various statistics such as mean and standard deviations are also, used to help us summarize the data. Now, when we're talking about the exploratory data analysis, or the EDA, they're saying data can be organized using a stem and leaf plot. And again, we saw that in the previous chapter. For calculation of central tendency or your average in EDA, we use a median for our exploratory data analysis. They're saying for measures of variation or dispersion, we use the interquartile range, which is, Q3 minus Q1. And so average is a median. For deviation, we're talking, or measure of dispersion, we're talking about interquartile range. So for graphically, we're actually talking about using box plots. And some textbooks might even call it the box and whisker plot, and you'll see why. But basically the idea is using these EDA techniques, we're of course trying to figure out, what information we can discover from our data. What is it telling us about, where the center of our data is, what kind of spread we are looking at, or what kind of variation, dispersion. And they're just talking about how EDA was developed by John Tukey, and this was presented in the book of the same title, Exploratory Data Analysis. So for us to be able to come up with these box plots, or the box and whisker plots, we are going to need a 5-number summary to help us out with. And you can see part of that is just the calculations we've already done. You find out what the lowest and the highest data value in our set is going to be, and then we're basically finding our quartile measurement. So we've got quartile 1, quartile 2, and quartile 3, or basically the median for quartile 2. So we are saying a box plot is basically going to be a graph of data, of a data set obtained by drawing a horizontal line from the minimum value, drawing a horizontal line from the minimum value to Q1, drawing a horizontal line from Q3 to the maximum data value, and then drawing a box whose vertical sides will pass through Q1 and Q3, and we would be drawing another vertical line passing through the median or Q2. So what they're basically saying, it's going to end up looking something. So we have a horizontal line going from the smallest data value to Q1. We have a horizontal line going from Q3 to the largest data value. And basically we have this box going from Q1 to Q3. And then in the middle, you mark where Q2 or the median of your data set is going to be. So we'll talk about this example, of course, once we get to it, but let's look at the procedure table again. Start with the 5-number summary. We only draw a horizontal axis and put your scale on the axis based on, the 5-number summary. The scale should start on or below the minimum data value, and it should end on or above the maximum data value. So we don't have to go like all the way from 0 unless that's part of our set, but just make sure you're giving yourself enough on the scale where the minimum and the maximum data values can be identified. Locate where the Q1, Q2, and Q3 values are going to be, the lowest and the highest data values, and then of course we go about drawing our box and whiskers, basically, if you will. So this example here is talking about the number of meteorites found in 10 states in the US. Obviously it helps to arrange them in order because we still have to find the quartiles. So putting them in order, we come up with our median, which is Q2 at 83.5. We've got our Q1 and our Q3 values. Of course, your lowest data value is going to be 30 and the highest one is going to be 296. So that forms our 5-number summary. We're drawing our horizontal axis over here, and since our lowest value is 30 and highest is 296, you can see they're going from 0 to 30 in increments of 100. And they're not really summarizing their 5-number summary, which they should, but your lowest data value is 30. Quartile 1 is 47. Quartile 2, which is our median, came out to be 83.5. Quartile 3 is 164, and then the highest data value is 296. So I know we have to go all the way up to number 300, but breaking this up into increments of 100 does not seem very beneficial because you can see those first 3 numbers are less than 100. It's between 0 and 100. So personally, I would have used a different scale, but that's what this example did. But you're basically going from lowest data value of 30. You will see again how we have that horizontal line. Once you get to 47 for your quartile 1, this is where we start drawing our box. We draw another vertical line at 83.5, which was quartile 2. Another vertical line at 164 for quartile 3. Complete that box, and then from quartile 3 till your highest data value, you end up getting the 296. So you have the box in the middle, and then those 2 horizontal lines is basically what they're calling as the whiskers. So basically, what does the box plot then tell us? Of course, you can see the median from that center line in the box. So they're saying if the median is near the center of the box, the distribution is going to be approximately symmetric, which is not the case in our example. If the median falls to the left of the center, then we would say our distribution is positively skewed. If the median falls to the right of your center, then we would say our distribution is negatively skewed. So just by looking at the line for our median, where it falls in the box, that can also help us. But sometimes it might even be helpful to look at the horizontal lines or the whiskers. So they're saying if the lines are about the same length, again, we can make the conclusion that we have an approximately symmetric distribution. If the right line is larger than the left line, which is what we have in this example over here, we would say the distribution is positively skewed. If the left line is larger than the right line, then of course we would say it's negatively skewed. So they're saying the box plot in the above figure indicates that the distribution is slightly positively skewed. So let's verify that. Our line for the median at 83.5 is towards the left of the center of the box. So of course that is telling us positively skewed. Our horizontal line on the right is longer than the line on the left, which is also telling us it's positively skewed. So yes, we can make the conclusion that our distribution is positively skewed. However, and you will see this in your example, sometimes the median line will tell you something else, and sometimes the horizontal lines will tell you something else. So then you kind of have to figure out which one seems to be more specific and what kind of distribution do we have. They're also talking about how you can do comparisons with two or more box plots or for two or more data sets on the same axis, and then you can compare the kind of distributions they have. You can compare the averages, you know, by looking at the location where the median of your graph is, and then how variable our data set is by looking at the length of the box itself. So what is your basic interquartile range in that case? So this example here is talking about the data shows the speeds in miles per hour of a sample of wooden roller coasters and a sample of steel roller coasters. So you can see those data values in there. So for each set, we would need to do the 5-number summary. And so you can kind of see we have our Q1, Q2, Q3. Same thing for the steel roller coasters, Q1, Q2, and Q3. And then of course, using your highest and lowest data values on the same horizontal axis, we've got both the box plots for our wooden and steel roller coasters. So of course you can see the steel roller coasters data set is more variable, right? Because that box is a lot wider than the one for the wooden coasters. And then you can also see how different the averages are, because the median for the wooden roller coasters is at 58, whereas for the steel roller coasters are at 85. So we know steel ones are definitely going to be faster than the wooden ones. So they're basically saying the box plot shows the median of the speeds of the steel coasters is going to be higher than the wooden ones. The interquartile range, or the spread of the steel roller coasters, is much larger than the wooden roller coaster. So we know that set is more variable. And they're saying finally the range of the speeds of the steel roller coasters is larger than the wooden roller coaster. So they're also looking at range. They're looking at interquartile range. And then of course, they're also looking at the median values. But in general, you can see we can come up with that conclusion that steel ones are going to be faster than the wooden roller coasters. And you could kind of have seen that even in the raw data if you would have just compared the numbers also. So you know that stands true. You can also have modified box plots, and they can and you can also use them to kind of check for outliers. So there's an example at number 19. If you kind of wanted to play around with it a little bit, you can take a look at that. So they're talking about an exploratory data analysis. Hinges are used instead of quartiles to construct box plots, and they're basically saying when data set consists of an even number of values, the hinges would be the same as quartiles. Hinges for a data set with an odd number of data values would be a little bit different from your quartiles, but they're saying, however, since most calculators and computer programs use quartiles, that's what we're going to be sticking with, is just the quartiles. So just to show you a comparison between if we were using the traditional versus the exploratory data analysis techniques over here. So we would be using frequency distribution in the traditional kind of calculations, of course, stem and leaf plot in EDA, histograms for traditional box plots in EDA, of course, mean in the traditional, median and in the EDA, and standard deviation for traditional, and interquartile range for EDA calculations. So let's go ahead and see if we can do a couple examples here from 3.4. Oops. There we go. All right, there we go. So let's do a couple examples over here. The first part is just talking about, identifying what our 5-number summary is, calculating the interquartile range. But since we'll be doing examples for that, we'll just go ahead and move forward. Now here they're asking us, seeing the box plot, will you be able to identify what those 5-number summary points and the interquartile range is going to be? So find the maximum, minimum values, the 3 quartile values, and your interquartile range. So looking at, I don't know, number 9, what do you think our 5-number summary is going to be? So let's start with the lowest data value. Quartile 1, quartile 2, quartile 3, and then the highest data value, and then our interquartile range. So for number 9, what do you think is going to be? Okay, Lily, you've got 55 for the lowest one. Okay. Let's see, Jesus, you're also giving us minimum at 55. Quartile 1, you guys gave us at 65. Oops. Okay, let's see, quartile 2, you had 70 and 70 for both of you. Okay. Quartile 3, both of you have 90. Okay, very nice. And that leaves us with the highest data value, which of course puts us at 95. All right, very good. So when you're talking about interquartile range, that's going to be quartile 3 minus quartile 1, which would of course then end up giving us 90 minus 65. And let's see, you guys have 25 as your interquartile range. Alrighty, very good. Yeah, good job, guys. So as you can see, some of these are going to be pretty easy to try and identify, but then some of them, if they were like at 67 or 88 or something like that, those kind of numbers would definitely be hard to identify. But when they match right with your scale, it definitely makes it a lot easier. So let's try and construct our own example over here. Let's look at number 13. So they're saying, okay, the data shows the population in thousands of the US colonies in 1700. They're saying Vermont was not a colony until 1791. And they're asking us to construct the box plot and decide if we have a symmetric distribution or not. So let's start by first putting this in order from smallest to the largest data value. So we're doing number 13. So putting this in order, what do we get? Okay, let me see. Okay, Jesus, you've got 2.5. And then you had 5.0, so that's 2.5 here. You've got 5.0, 5.7, okay. Then of course 5.9 would be next. And then let's see, what did you have after that? 10.7, okay, I see that. And what was your next one? 14, and then 18. Okay, 10.7, 14.0, 18.0, and then you've got 19.1, okay. That will then bring us to 26 and 29.6, okay. And I think that just leaves us with the 50s then after that. So 55.9 and 58.6. And I think that covers all of those numbers. So the last two, 55.9 and 58.6. All right. So go ahead and tell me what our 5-number summary values are going to be. And of course, we'll need the IQR also. Of course, we know the minimum is going to be 2.5, maximum is going to be 58.6. And you've only got 12 colonies in here, like they said, since Vermont did not come in till much later. Alrighty, let's see. Jesus, you've got quartile 1 as 5.75, quartile 2 at 16, okay? So we've got 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So for quartile 2, you would actually end up taking an average between 14.0 and of course 18.0, which is coming up to be 16.0. And since they are keeping everything at 1 decimal place, we'll kind of follow the same rounding as them. So once you have your median, which is going to be right here, that of course tells us you are going to have to use all of these first 6 data values for quartile 1 and the second 6 data values for quartile 2. So since these are 6 values, of course, that means we end up taking an average between 5.7 and 5.9 for quartile 1. For quartile 2, we will end up taking an average between 26.0 and 29.6 for quartile 3. So you're still getting 5.75 for quartile 1. So that's 5.7, plus 5.9 divided by 2, which is actually coming out to be 5.8, which makes sense because you're halfway between 5.7 and 5.9. Quartile 1 should be 5.8. Quartile 3, of course, you are again taking the average between 26.0 plus 29.6, dividing that by 10. Let's see, Jesus, you had 28.7, so let's see. So you had 28.7. Jesus, I'm coming up with 27.8. Okay, Jesus. So you've got your 5-number summary now. For interquartile range, we would be taking quartile 3, which is 27.8, and subtracting quartile 1, which is 5.8, and what will that come out to be? So what's the IQR? It's not 22.95 is what Jesus has on his answer. If you just ignore the 0.8 and 0.8 on both the numbers, you're basically just having to subtract 27 minus 5. Yeah, very good. It should be 22. So Jesus, just be careful. Looks like your calculations are just slightly off here. Okay, so we have our 5-number summary. We have our interquartile range. So now we're ready to graph our box plot over here. So of course we start with our horizontal axis. All right, so let's do that. Over here, and then we need to go from the smallest value of 2.5 to the largest value of 58.6, and of course we're looking at 5.8, 16, 27.8 as the numbers in between. So what kind of scale would you use on your horizontal axis over here? We can't start with 0 in this case, since 2.5 is our smallest value, and probably go up to 60 since we've got 58.6. So how would you break up that scale on this horizontal axis if we're going from 0 to 60? Would you do it in 5s or 10s? 10s, Kimberly, okay. If we did this in 10s, then we would have 0. And obviously you want to make sure they're spaced out at an equal distance from each other. So if this is 0, maybe 10, 20, 30, 40, 50, and maybe 60 over here. So at 2.5, which just to kind of show you, halfway would be 5 and half of that would be 2.5. So we could do 2.5 over here. For quartile 1, we are at 5.8. So if 5 is the halfway mark, 5.8 is just a hair after that. So I'm just going to put a little bit of a vertical mark so I know that's where my box will begin. For quartile 2, we have 16. So of course 16, 15 would be the halfway mark. So we would be marking 16 just again, maybe a notch after that. So I'm going to put another vertical mark for my quartile 2. Quartile 3, we are at 27.8, so close enough to 28. So again, of course, halfway mark would be 25. If we did another, so 25 would be the halfway mark. If we did another halfway mark, that would be 27.5. So as you can see, again, we will be just a little bit after that. So you can put another vertical mark for the 27.8. The maximum value is 58.6. So again, halfway between 50 and 60 would be 55. Half of that would be 57.5. So maybe again, another notch from there would be your 58.6. And for that 58.6, we're actually again just going to put a dot for that. So once we have this, and again, it definitely helps to have, you know, good, nice straight line. So we can do a vertical line. Oops. Not what I was wanting to do. Okay. The vertical line over there, I'll do another vertical line here. And a vertical line here. So this will form our box. We will need to do a horizontal line, which will go from quartile 3 to our maximum value. We would need another horizontal line, which would go from quartile 1 and the lowest value. Oops. Can't draw horizontal lines. Okay, so, and then complete the box over here. Now, since these numbers are so unusual, and as you can imagine, we will not be able to identify the numbers just by looking at our box plot. So it actually makes sense to go ahead and write all of these down. So our minimum was at 2.5. Quartile 1 was at 5.8. Quartile 2 is at 16.0. Quartile 3, 27.8. And then, of course, our maximum value was at 58.6. So it's definitely the good idea to label, I guess, our points on this. Now, can you say that this is a symmetric distribution? There's not really, I mean, the box, you could make the argument, yes, the median line is kind of in the middle of the box, but then when you look at those whiskers or the horizontal lines on each side, it definitely does not give us the impression of being symmetric. So what kind of shape would you say this distribution has? Positively skewed, negatively skewed? Okay, let's see, Jesus and Lily. Alexander, positively skewed. Yeah, very good. Because again, just to show you, where's our little table over here? There we go. They were saying when the right line is larger than the left line, we say it's positively skewed. So we're looking at 2b over here, and that's exactly what our example has. So we would say the distribution is positively skewed. So as I was saying, you know, sometimes your box may be showing one thing and then your lines, horizontal lines, could be showing another thing. So you kind of have to then decide which one seems like a more appropriate distinction for our distribution shape. Alrighty. Any questions on this example over here, guys? Now, you know, of course, as you've seen with chapter 2, you will be doing your box plots on the Connect mat. So they're going to do a lot of the setup for you. But if you had to do these by hand, again, you should be comfortable coming up with the box plot on your own. And I think that's similar to what all of our other examples here end up looking like. But let's go ahead and well, all of them look very similar. It just looks like they're using just whole numbers or decimals instead of that. Are you guys comfortable with this, or would you like me to do another example? Okay, Maya, Tyler, Kimberly. Lily, I can't see you. I don't know where you went. Ah, there you are. Okay. So the rest of you, did you guys want to see an example, or you're comfortable with this? Alexander, you're okay? Yeah. Jesus? Okay. Lily, you're okay as well? Yeah. Okay. Alrighty, guys. So as you can see, that 3.4 section was not really very big. We just talked about the 5-number summary, and then we looked at our box plots. And then, of course, just remember when you're doing a comparison box plot, you just need to have one horizontal axis. So just have the one horizontal axis, and then one on top of the other. You're going to have your 2 box plots. Okay, so I guess that will then take us into section 4.1. So far we have actually been talking about, descriptive statistics. Now we are getting into what we call as the inductive, not inductive, inferential statistics. And this is where we start talking about probability now. So we're starting out with our probability and counting rules. So, they're talking about basically what kind of a chance an event has of happening. So they're saying from the time you wake up until you go to bed, you make decisions regarding the possible events that are governed at least in part by chance. So should you carry an umbrella to work? Will your car battery last until spring? Should you accept a new job offer? Those kind of things. So we're going to be looking at like different calculations, different techniques of how we can come up with our probabilities for, similar kind of examples. So we're talking about probability as a general concept, can be defined as the chance of an event occurring. So what is the chance this will happen? We talk about probability in terms of, from observing to playing games of chance, such as, card games, slot machines, for that matter, even lotteries are based on chance. We can also use probability in fields of insurance, investments, weather forecasting is definitely a big one. So you have games of chance, like we talked about card games, slot machines, and lotteries, but insurance is definitely one of the bigger areas where we actually use this probability to see what kind of insurance premiums a person has to pay. So, that's why they always look at like, are you a young person? Are you a new driver? Because being inexperienced, you're going to have a higher premium because, there's a chance, the chance of getting into a wreck is going to be a lot higher than maybe somebody who's been driving for 10, 20 years. So insurance is definitely one of those. If you invest in like stock market and stuff, you're always kind of seeing how these stocks are performing over time, to try and see, okay, is this something we want to do? And then weather forecasting, they'll always tell us there's a 20% chance of snow or a 70% chance of rain and that kind of thing. So again, this is all based on probability in this case. So we're talking about probability is basically coming from the study of inferential statistics. Predictions are based on probability, and then hypothesis testing actually also uses probability, and hopefully we'll get to talk about that. So just as some basic concepts of probabilities here, we're talking about probability experiments, sample spaces. We will be talking about addition and multiplication rules. And we will also actually look at how we can find probabilities of complementary events, because sometimes it's easier to find the probability of the complementary event than of the actual event itself. So we'll talk about that. Also, we will also look at counting rules. We'll look at permutations and combinations. And again, some of you must already be familiar with these calculations. So the first thing we're actually going to start out with, guys, is our sample spaces, because if we're talking about calculating probability, then we actually need to know what our sample space is going to look like. This one is talking about the theory of probability grew out of the study of various games of chance, such as, flipping a coin, rolling a dice, or, of course, your card games. So they're talking about processes such as flipping a coin, rolling a die, rolling a card, or sorry, drawing a card from a deck are what we call as probability experiments. So just as your definition, we're saying a probability experiment is a chance process that leads to well-defined results called outcomes. When we're talking about an outcome, we are saying it's the result of a single trial of a probability experiment. So think about if we were flipping a coin, right? That's the probability experiment. The outcome would be, does our coin land on heads or tails? So that would be the outcome. If we're talking about rolling a die, then the actual process of rolling a die is what we call as the probability experiment. But then does your dice land on the number 1, 2, 3, 4, any of those numbers? Those would be our outcome. So you can kind of see in this little paragraph here, we're talking about tossing a coin has 2 outcomes, head or tail. We're talking about excluding the possibility that the coin would land on its edge, because obviously that does not count as an outcome. When we're rolling a single die, we're talking about our outcomes could be anywhere from the numbers 1 to 6. And of course, we're assuming it's a die that has 6 sides. Now, of course, you have dice that also have sides more than just 6, but we're just sticking with the standard die over here, which would be 6 faces to it. If you talk about drawing a card from a deck, then, of course, you would be talking about a lot more outcomes, because you would be looking at your suits, which have the clubs, the diamonds, the hearts, and the spades. So, of course, then we would have more outcomes. But just as an idea, when you take all the possible outcomes that you will get from this probability experiments, that entire set is basically what we call as a sample space. So think about this. If we are talking about tossing a single coin, then our sample space will only have these 2 outcomes of a head and tail. Just like we talked about with the roll of a die, you would only have 6 outcomes in our sample space. So all of those possibilities become our sample space. They're talking about if you had a true and false question, then of course you can either answer the question as true or false. So both of those outcomes would become part of our sample space. And the last one here is looking at, okay, what if we are tossing 2 coins? So that means, of course, each coin could still land at a head and a tail, but looking at them together as an outcome, both the coins could land on a head, they could both land on a tail, or the first one could be a head, the second one could be a tail, and the second one could be a tail, and the first one would be a head. And these last two outcomes are going to be 2 separate outcomes. They are not the same, because it's the idea of which one of them landed on the head and which one landed on the tail. So that's why we have to write them as 2 separate outcomes. So that's kind of how you come up with your sample space over here. And they're kind of talking about that here in this little paragraph over here, so you can kind of read that if you like. So just like that, let's say they were asking us to find the sample space if we were going to roll 2 different dice over here. So of course we know each one of the dice has 6 different outcomes. They could both land on a 1, they could both land on a 2. The first one could be on a 1, the second one could be on a 6. So you have all of these different combinations that you come up with. So we have to then list each one of these out. So if you look at the sample space, and I'm not sure how clear those numbers are for you, but we're putting them as though we're writing them as sets of ordered pairs. So we're basically saying Both of our die could land on number 1. The first one could land on number 1, the other one number 2, and you can go down the whole list of the first one being 1, but the second one being a 6, or you can say the second one could land on a 1, but the first die would be going to different numbers. And so you can see we have a total, and if you just multiply, we have 6 options on our rows, and we have 6 options on our columns. So if you do 6 times 6, you actually have a total of 36 different outcomes in this sample space, because you are now rolling 2 die. If you were just rolling a single die, you would only have 6 outcomes. But you can see the moment we roll 2 dice, we now have 36 different outcomes. And this is going to be true for a lot of these experiments if you're going to bring in multiple items in there. In that same way, they're talking about what is the sample space going to be if you are drawing 1 card from an ordinary deck of cards. When they say ordinary, they're just saying it's going to be standard. It's not going to have any extra cards in there. Of course, we're not counting, you know, the Joker cards and all of those. So just your 4 suits, and each suit would have 13 cards in there. So again, if you just multiply 4 times 13, you can see we will end up getting 52 different outcomes. And then of course your cards go from an ace, then the number cards going from 2 through 10, and then of course you've got your Jack, Queen, and King, and then for all 4 of the suits, and this ends up giving us 52 different outcomes. So this sample space is going to have 52 outcomes. So just remember, sample space is the idea of what possible outcomes we can have. It's just talking about just making sure we are considering all the different possibilities that we can get if we were going to draw a card from our deck of cards, or if we were going to be rolling 2 different dice, or if we were going to be, you know, flipping multiple coins kind of thing. So this example here is pretty interesting, number 3. They're talking about creating a sample space for the gender of children in a family that has basically 3 children. So we're of course using B for boy and G for girl. So the idea is, if we're talking about 3 children, again, what kind of combinations can you have? All 3 of them could be boys, all 3 of them could be girls, but then you could also have combination of 2 boys. Yeah, these are all 2 boys, or you could have a combination of 2 girls. But you will notice that these 3 are not the same outcome, because is the first one a boy, is the second one a boy, is the third one a boy. So because, you know, they can be the firstborn, the secondborn, and the lastborn, you have to consider all the different options you have over here. So we cannot say BBG is the same as BGB, because that means the first 2 were boys and the last one was a girl, whereas the first and the last were boys and the middle child was a girl. So again, you can see how we have to consider these as different options. Now, you know, just coming up with a list of what those 3 children can be, this can actually take a little bit of work if you're just going to be looking at this from, okay, what combinations do we need to go through? But there are easier ways of coming up with these list of options, especially in an example like number 3, where we're talking about like a gender for children. So in this case, of course, we will have 8 different possibilities. So we're talking about, from examples 1 through 3, the sample spaces were found by observation and reasoning. However, another possible way is to use a tree diagram, and that's what I normally use when we're trying to do these kind of examples, because it really kind of helps you visualize what options we can be looking at. So this one here is talking about a tree diagram is a device consisting of line segments emanating from a starting point and also from the outcome point. It is used to determine all possible outcomes of a probability experiment, and this is actually what a tree diagram looks like. So this is our same example with a family that has 3 children, and we want to know, you know, how many boys and girls they can have, coming up with our sample space. So you can see we start from our starting point, we go into 2 directions. the first child could be a boy, and the second one could be a girl, right? So that's the option for our first two, for the very first born. After that, let's say they had a boy, this family had a boy, which means, again, for the second child they again have to break it up into two options where they could have a boy and a girl. Let's say they ended up having a boy also as their second child, then that means for the third one, again, we would need to break it up into two parts of boy and girl. So they started out with boy for the first child, boy for the second one, and let's say they ended up with boy for the third one, that would be all three boys. BBB would be our outcome. If they had a boy and boy for the first two, but then for the third one, they ended up having a girl, which would give us this option, right? Let's say they did not have a boy and they ended up having a girl for the second option. So again, that means for the third one, they could either have a boy or a girl, and that would end up giving us these two outcomes. So basically, that's what a tree diagram does, is it helps us come up with all the different possibilities that we have in this example. And so, when in doubt, when you're just, trying to come up with it, try a tree diagram and see if it helps you come up with this sample space that we are looking for. They are also telling us in many problems, one must find the probability of two or more outcomes. And for this reason, it is necessary to distinguish between an outcome and an event. When we're talking about events, we are saying an event consists of a set of outcomes of a probability experiment. So your event will also actually contain a set of outcomes. So, going back to our kids example over here, if they said, in the event that this family has two girls and one boy, how many outcomes there are going to be? Well, think about this. We are talking about two girls and one boy, which would be three different outcomes. So then we would say there are three outcomes in this event. So the event and outcome are definitely not going to be the same thing. So let's see if we can find an example in here. We're coming up with our own sample space. Okay. They're gonna have us do okay, like something like number 25. So they're telling us, and this is very similar, of course, to the example we just looked at, but they're saying, okay, a couple has 4 children, and they're asking us to find these probabilities. So, if you were going to start solving an example like this, you would, of course, need to first figure out what are the different possible outcomes for this couple that will end up having 4 children. So if you think about it, that would just be an extension of this graph that we just looked at. Now you were already at the third child over here, which means now from these last answers that we have, each one of these would then need to be broken down into 2 more options. Again, that boy girl option, till you could figure out, how many different possible outcomes you are going to have. So again, just a kind of a build up on this example. Any questions so far in terms of what is a sample space, what is an outcome, and what is an event? Okay. Okay. Alrighty. So again, coming back to our discussion for an event, we're basically saying an event can be one outcome or it can have more than one outcome. So like I was talking about in this example, what if you were looking for 2 girls and 1 boy? That definitely gave us 3 different outcomes. They're also saying an event with 1 outcome is of course called a simple event. And if you have 2 or more outcomes, then we call it a compound event. we're actually going to talk about this a little bit more in detail tomorrow, but they are also talking about how there are three basic interpretations for probability. So we'll talk about what is classical, empirical, and subjective probability, and we'll kind of look at the differentiation between them. So we'll pick up from this here tomorrow. So for today, we're definitely done with chapter 3. So if you will quickly go ahead and tell me when you want to take your exam, I'll go ahead and set it up for all of you. So do you want to take it? I don't know if you guys are done with all of your homework or if you need time to finish your homework and your quiz. So if you will just go ahead and send me your time over here, I will set it up for you. Okay, Jesus, you said 9 p.m. Lily, right now, okay, so I'll do that right after class. Give me about 5-10 minutes to set it up, okay? Tyler, you're also saying now. Alexander, you said 3 p.m. Maya, I'm kind of hoping you can do it today, but if you have something else going on, you can do it before class tomorrow, but I don't want to push it later than that. Kimberly, you're saying tomorrow at 9:30. Okay, so that should give you about 2 hours before class time. So hopefully it should not go any longer than that. You should be okay. All right, so I've got Tyler at right after class, Lily right after class, Alexander, I've got you for 3 p.m., Jesus for 9 p.m., Kimberly tomorrow morning at 10, and I think you should be enough, because if I gave you the maximum time, it would still be 1.5 hours. So I think you should be okay if you started at 9:30. Okay, so Maya, I'm just waiting for yours, and you said I'll just do it now then. Okay, alrighty. So those of you who are doing this right after class, give me about 5 to 10 minutes to set it up, okay? All right, everybody, be careful, be safe, and I will see you tomorrow morning. Take care, everyone. Good luck. Bye-bye.